Okay, so let's go over this exam review right here. So first thing, what is the sign of delta H in an exothermic reaction? Well, exothermic, it's releasing or losing energy. It's always negative. Let me write the answers in. What color do we want to use today? Let's use orange. Sure. So exothermic is negative. Endothermic is positive. Okay. Heat flows into the system, it enters the system in endothermic. Heat flows out of a system, it exits in an exothermic. A calorie is the energy required to heat 1 gram of water by 1 degree Celsius. 1 gram of water to heat 1 gram of water by 1 degree Celsius. That is the definition of a calorie. We're going to shrink it and move it. Oh, where'd it go? Okay, the energy needed to heat 1 gram of water by 1 degree Celsius. Make it orange. Make it all orange today. Why did it do that? Okay, what is a calorimeter measure? Calorimeter measures the number of calories in a chemical reaction or physical change. So calorimeter measures number of calories. Associated with chemical or physical change. Okay, let's convert the following. I wish that would just stay there, but whatever, it's not going to stay there. We're just going to forget it. Okay, joules to calories. So 34.6 joules, so 34.6 joules. And there is 1 calorie is 4.184 joules. Okay. And you get 0.827. Okay. Big C calories to little c calories. This is, you just got to divide by 1,000 basically here. So 1 calorie, or actually multiply by 1,000. Sorry. My bad. It's 1,000 calories for every 1 big C calories. So it's 7,800 calories with the lowercase c. Kilojoules to calories. This one takes 2 steps, so we got to go from kilojoules to joules. So 1.23. I didn't really tell you how to do this, did I? Don't worry about this one. Why did I even do this one? Yeah, don't worry about. I guess we can do it. We'll do it. We'll do it. It's not that hard. So 1.23 kilojoules. And we got to go to joules first. So there's 1,000 joules for every 1 kilojoule. And then there's 1 calorie is 4.184 joules. So do it that way, 1.23 times 1,000 divided by 4.184, and we get 294 calories. Well, let's make sure we box all our answers. Okay, and then the last one here, calories to joules. That one's simple. It's just actually 23 calories. There's 4.184 joules per calorie. 2.3 times 4.184 basically. We get 9.6. Okay. Next one, what's the law of conservation of energy? That is, energy cannot be created or destroyed. But can be transformed from one form to another. Simple, simple. Okay, what's the difference between heat capacity and specific heat capacity? Heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Celsius. Okay, so that it really doesn't depend on mass. It's kind of like it does vary with mass. Heat capacity varies with the mass of the object. Okay, heat capacity varies with the mass of the object. The object, if it changes mass, its heat capacity changes. Okay, so that one does vary with mass. So which one varies with mass? Heat capacity. Specific heat does not vary with mass. It's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So 1 gram of a substance by 1 degree Celsius. So specific heat mass doesn't matter. Okay, doesn't matter. Specific heat is a property of a type of matter. It doesn't change as the mass changes. Okay, negative Q means that we're losing energy. It's exothermic. This other one should have said positive Q. Whoops, I'll change that. I'll fix that. But positive Q is endothermic. My bad. I copy and pasted that one and I forgot to change it. Okay. So positive Q is endothermic, negative Q is exothermic. Endo or exo? Well, this one is more energy in the end. There's more energy in the end than we started with. So that means it's endothermic. It took in heat. took in heat energy. Hi, Kiki. My cat wants to say hi. Hi, everybody. Okay. Does this graph represent endo-exo? So this one, the products have less energy than the reactant, so it released energy, so it's exothermic. What is the definition of energy? Energy is the ability to do work or produce heat. Oops, ability, do work or produce heat. Which direction does heat flow? Heat flows from hot to cold always. Or high concentration to low concentration. Hot to cold. Okay, so we're looking at this heat and phase change of matter graph here. What are these different points? A represents the solid phase. B represents the liquid phase. And C represents the gaseous phase. Make this easier. Okay. D, if we're going from liquid to solid, that's freezing. E, if we're going from solid to liquid, that's melting. F, we're going from gas to liquid, that's condensation. And G, we're going from liquid to gas, that is vaporization. Okay, a stone is heated and placed in 1 liter 1,000 grams of water. The temperature rises from 20 to 30 degrees Celsius. How many joules of heat did the stone release? So this we're just using Q equals MC delta T. And we know all of these things. We just got to find Q, right? So the mass of the water is 1,000 grams. Okay. The C of the water is 4.184. And the delta T of the water is 30 or 20 to 30, so 30 minus 20. So that's 10 here. So it's basically 10,000 times 4.184 or 41,840 joules, which is 41.84 kilojoules. Next one, we're using delta H of fusion. So how much energy is gained or lost when 10 grams of water freezes at 0 degrees Celsius? So it's at its melting point, so we don't have to worry about too much. We don't have to worry about all the different steps. We can just do it in one step here. So 10 grams. The problem here is that we actually have, it's in kilojoules per mole, the delta H of fusion. So we got to convert that to moles first. So 1 mole is 18 grams. So 10 over 18. Let's see, what is that? And we get 0.56 moles. And then we just multiply that by the delta H of fusion, which is 6.01. And we get 3.34 kilojoules. And this is water freezing, so it has to release it, so it's negative. So it's released. So negative 3.34 kilojoules released. Okay. Continuing on here. Oh, hi, Kiki. Sure. Okay, next one. Which of the following is equal to the delta H of vaporization? So the opposite of delta H of vaporization is delta H of condensation. That's the opposite. So if you have the negative delta H of condensation, that would be the same thing as that. Those two things are the same. They're equal and opposite. Give 5 examples: endothermic and exothermic reactions. Just go back and review the worksheets that we gave examples of. So just go back and review those things. I'm not going to go through all of them. Okay, number 20. Calculate the amount of heat needed to melt 18 grams of ice at negative 20 degrees Celsius. Okay, so first of all, we have to heat the ice from negative 20 to 0. Okay, we got to heat it first, and then we can melt it. Okay, so to go from negative 20 to 0, we got to use Q equals MC delta T. Okay, so mass is 18. The C of ice is, oh, that's not 4.184. I got to change that. That's not true. The C of ice, let's find it actually real quick. I know it's in, let's see, what assignment is it in? This one. It's in this one. So I'll have to change that on the worksheet here. If you did it with 4.184, it's fine. That's the one I gave you, but that's not really true. It is 2.09. So let's use the real one. So 2.09. So this should be 2.09. And then delta T is, we're going from 0 or negative 20 to 0. So final minus initial. Okay. So we do that. We 18 times 2.09 times 20. And we get 752.4. And that's in joules. So just be careful that that's in joules. Let's convert it to kilojoules. So divide by 1,000. So 1 over 1,000. And you'll get 0.752 kilojoules. Okay. In order to melt it, again, we're using the delta H of fusion, which is 6.01 kilojoules of energy per mole. So we have to convert that 18 grams to moles. So 18 grams, and then it's 1 mole over 18 grams. So it's actually just 1 mole. So 1 mole times the 6.01 kilojoules per mole. Super easy. We get 6.01. So then we add these two things together. So you get 6.7624 kilojoules needed. Okay. Kiki just wants to say hi a lot today. Okay, all right. These are the fun ones. These are the ones you guys love to hate. Okay, so this one's what we call Hess's law. We're combining these equations here to form these 3 equations to form this equation up here. So first thing, I'm going to look at this one, C2H6. And we have C2H6 here. So we can leave this one alone. I'm just going to leave that one alone. Next thing, we have C2H4 gas. Okay, and we have C2H4 gas here. So it looks like we can probably leave that one alone as well. Okay, I think what it's going to come down to is what do we need to do to this one to eliminate H2O and all the other things, right? And let's see. Oh, whoops. I got to flip this one, don't I? Someone should have said that. I got to flip this one. I got to flip it. This one's in the reactants, that's in the products. I got to flip it. So we're going to get 3H2O plus 2CO2 yields C2H6 plus 7 halves O2. And now our delta H now is positive 1560. And we can get rid of that one. Okay, now we have now it's in the right spot. Whoops. Wasn't in the right spot before. Okay, now we'll see that we can cancel out 2 of these and 2 of these. So that's 1 H2O here. The 2 CO2s cancel. The 7 halves O2 and the 3 O2 cancel, and then the half O2 will cancel. So actually, we don't need to do anything to this one here. We can leave it. So the only thing we need to do is flip that first one. Leave it alone. And that will make the H2 here an H2, right? And then this H2O here and these H2Os will cancel. They're opposite sides. The CO2s will cancel. They're opposite sides. These O2s add up to 7 halves, and those will cancel on this side. Okay, so the overall delta H would be this one plus this one plus this one. So overall delta H equals, hold on, 1411 plus 1560 plus negative 285.8, and I got negative 136.8. So that would be the delta H for this reaction here. Easy peasy. Okay, enthalpy. Enthalpy is the total heat energy of the system, or yeah, it's basically the heat energy of the system. So you can just look at that definition. I don't feel like writing it all out, but okay, next one. How much heat is absorbed when 525 grams of water at 100 degrees Celsius is converted to steam? So it's at its boiling point. So this one's a little bit easier. Delta H of vaporization is 41.7 kilojoules per mole. So just careful here. This is in grams, so we have to convert that to moles first. 525 grams, then 1 mole over 18 grams. We'll get the number of moles. So 525 divided by 18 is 29.2 moles. And then we just have to multiply that by the 41.7 kilojoules per mole. And then we get about 1,216 kilojoules. Okay, almost done, almost done, almost done. Bunch more. Okay, next one, calculate standard reaction enthalpy. So this one we're using the delta H of the formation for the products minus the reactants. So the products here, we have C6H12O6, which is negative 1274.5 kilojoules per mole, and there's only one of them. Plus 6O2, and now O2 is just 0. Okay, and then we subtract the reactants, the sum of the reactants. So the reactants, there's 6 CO2s, so 6 times negative 393.5. Plus, there's 6 H2O liquids, so 6 times H2O liquid, which is negative 285.8. Okay, so we just got to do that math there. 6 times 393.5 plus 6 times 2. Okay, so this, when we do this and this together, you get 4,075.8. And that's negative. Okay, so essentially we're going to add this to this. Okay, and I get, when I get this, I get 2,801.3. Next one, 25. When 1 mole of methane is burned at constant pressure, 890 kilojoules is released. What's it for 10 moles? So 10 moles, this one's super easy, 10 moles times 890 kilojoules for every 1 mole. So you get 8,900 kilojoules. Super simple. Next one, heat 10 grams of H2O from 10 to 25. This one just Q equals MC delta T. So MC delta T. And you get 627.6. That's joules. Okay, 27. What is the specific heat of a substance? Has a mass of 5 grams, and it's heated from 15 to 35 with 546 kilojoules. Joules of energy. So we have 5. So Q is 546. M is 5 grams. C is what we're looking for, and then delta T is 35 minus 15. So we're solving for C here. So we can divide by 5 times 35 minus 15. And that will cancel on this side. We'll get C by itself, but we got to do it to both sides. So 5 times 35 minus 15. So C equals 546 divided by 5 divided by 20. So 5.46. That's joules per gram degree Celsius. Okay. Last one. So a 40-gram sample of metal with a specific heat of 0.43 joules per gram degree Celsius is heated to 100 degrees Celsius, then placed in a 100-gram sample of water at 30 degrees Celsius. What is the final temperature? So we've seen lots of these problems. It's just negative Q of the metal, because it's losing heat, is equal to Q of the water. The negative Q of the metal is going to be M of the metal, so 40 times C of the metal, which is 0.43. And then delta T is T final minus initial temperature, which is 100. So that's the metal. The water is 100 times 4.184 times T final minus the initial temperature, which is 30. Okay? So I'm going to multiply these two and then distribute. Same thing with this one, multiply these two and then distribute. So 40 times 0.43 is 17.2. And then 1,720. That's all negative. And then, so 418 TF minus, so times 30. And we get 12,552. Okay, and then don't forget distribute this negative sign. So negative 17.2 TF and positive 17.20. Then I'm going to add 17.2 TF to both sides. And I'm going to add 12,552 to both sides. We get 14,272. And this one, we get 435.6. One more step. We just got to divide both sides by 435.6. TF equals whatever that is. 32.8 degrees Celsius. Does that make sense? It's 30 to 32.8. That makes sense. Okay, that's it. That's all the answers. Are there any problems that you guys were confused on that you want me to go over again and explain better? Or do you feel that it's okay? Okay. Okay. Thank you. Well, that's all I had. That's all I wanted to do today. So if you do have any other questions for you, for your own personal self, please do stick around and ask. Otherwise, you all are free to go. If you came in late, just stick around. Make sure I get you for attendance. Okay. Yep. Have a good day. Okay. Have a nice day, Tyson. Luke. Okay, Lukel, I got you. Later, Sienna. Bye, Zoe. Bye, Casey. Bye, Harley. Later, Devin.